extra strong.
Roman concrete.
Fully hydraulic.
Structural
Molded connections.
It's the
Structural engineering
podcast.
Hello, welcome to this week's episode of the Structural Engineering Podcast. My name is Max,
And I'm Zach.
and we've got a real special episode. We're doing another interview this week. We got to sit down with Patrick McManus of Martin & Martin Consulting Engineers, based, I think, out of Denver, right? They're a Colorado company.
Right.
And a really good one. So it was a pretty cool conversation with him. But before we jump into that, we got a news of the week. What do you got, Zach?
Yeah, so this week an article came out talking about performance-based wind design. And I think this is something that is going to change wind design in the next 10, 15 years. Right now, the Tall Building Council for ASCE is kind of putting together a census letter, kind of going through what that means. But if you have odd-shaped buildings, super tall buildings, it's going to change a lot of what you're doing. And I think that's something we'll kind of start understanding more and more as time goes on, and we'll keep updating that through this podcast. Something else that's super interesting that I just found out about wind design beyond this, maybe encapsulating this as well, is that in the future they're looking to use ductility for highly loaded buildings. With high wind loads, tornadoes, hurricanes. Right now, the code has you just design it really, 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 really hard. Like super heavy loads. There's zero ductility that you can account for when looking at your wind loading. But they're looking at in the future to be able to account for that in these huge,
catastrophic
events.
Tornado. That's cool.
What do you think?
I like it. I'm into that, totally.
I'm super into it. I think that will start, you're pretty much going to have an R factor, your response modification factor for wind.
Oh, yeah. Absolutely.
And I think you'll start maybe going away from an RF3 system in super high wind-loaded areas because you want some ductility in there.
That's going to be cool. I don't know how that'll look.
I think it'll be so awesome.
That'll be so fun.
Since this podcast is basically just all about seismic loading because it's the best loads out there.
Anyway, let's go to tip of the week on that.
All right, Max, what do you got for the tip this week?
We're talking about multi-tier brace frames. So this is a brace frame that you might imagine in a tall warehouse or in some sort of atrium where there are multiple floors on one side, in this atrium example, but you have a lot of glazing on the other. And if you have a brace frame going up the whole height of the building without tying into the diaphragm anywhere, you need to support that with a little additional load coming down from the brace.
Yeah, so that's where you start designing for this out-of-plane load on your column. So you have these super tall columns. Every point at which that brace intersects the column, you'll have a beam that comes across. But at each node, you'll have to design for an out-of-plane load of 0.006 times the axial compression load in that brace.
Is this new a ISC 16?
Yeah. So this is something new to be within the code and have an expanded section on it. This is not something new to engineering.
You could have a multi-tier brace frame.
You've always been able to have one, but it's now within the code that gives direction on how to design for it. And what they found through a lot of testing, some earthquakes, is that there's this kind of second order little P delta effect, non-linearness that's happening here, so that those columns are starting to want to buckle when they start getting really heavy loads. There's nothing to resist them from moving, right? When you have your floor diaphragm come out, that compression load comes down. If there's anything out of plane due to that compression load coming into your column, it's resisted by the diaphragm, and maybe a beam framing into it. But in these scenarios, you don't have that happening, and so your column's going to try to buckle.
There you go, 0.6% axial load of the
and that is at every single node.
Yeah.
So if you have a super highly loaded brace, system or bay, you can get some pretty massive out of plane loads that are going to upsize your column. So I think this is something to really think about when an architect says, "Hey, what if we pulled back all the floors that are going out to this brace?"
It would look cool.
And I think that happens a lot. So if you're in a high seismic system, and especially as a young engineer, it's something to think about. If you have a multi-tiered brace frame, you should go, I wonder if we're going to have some out-of-plane loading on this, and maybe that's going to upsize your column a couple sizes.
Sweet. That's a good tip.
So let's dive into this week's topic, Max.
Let's talk to Patrick.
My name's Patrick McManus. I'm a structural engineer, principal with Martin & Martin, is one role that I serve. I've also worked for the steel fabricator Puma Steel, who's a mid-sized fabricator in the mountain region, managed their engineering and detailing, which actually got us involved in some of the early seismic work that I did. Worked with BRBs. We did some bolted testing for Star Seismic back in the day when they were getting qualified. And then I started a venture called Novel Structures, where our focus was to develop a seismic fuse. It's a component in brace frame systems, and that's most of my background, other than being heavily involved in AISC. I'm on the seismic committee through them, as well as the committee on research and the CPRP Connection Pre-Qualification Review Panel. So.
Nice.
Very cool. Yeah.
Yeah, we actually listened to a webinar. We did a podcast on R3 versus 325, and one of the things we listened
yeah.
to, Zach realized
Yeah.
today that was your presentation, the foundation savings.
That's exactly it. I mean, really, that's what started this. When we did the work on the BRBFs, working with Star Seismic on that, we really wanted to start using those in non-seismic regions. The region being that large R, using an R of 8 versus an R of 3 cut your foundation forces down so substantially that made a lot of sense. As it turned out, BRBFs weren't the best animal for that, because you really can't get a brace that's manufactured with a strength less than about 100 kips. So all the overstrength to develop that brace makes it sort of cost prohibitive.
Yeah.
So that sort of led us to, hey, it'd be great if we had something that performed about as well, but actually hit the force range below that. And that sort of led to Refuse. That was some of the genesis behind it.
Interesting. That makes sense. When did that idea sort of come up? You know.
It really was when I was with Puma. We worked on the San Joaquin Administration Building, and we were using BRBs in that building. Puma's a bolt shop and wanted a bolt, which is not normal out on the West Coast. And so the engineer of record, Pat Crosby, who's a very progressive guy, was like, well, I'm not against it, but just show me one test where somebody has done all bolted connections. And we couldn't find one. So we did one. But then that's when we started circling around to this overstrength being a little bit of an issue. We always saw the value in trying to use the high seismic systems out here, primarily because of that we were watching the codes progress, and in our design practice, we noticed that seismic was governing more often than not. It used to be that you just checked base shear, and if wind governed over seismic, you were done and on your way. Now the codes have become much more complicated than that, right? I mean, you can have base shear govern in wind and not seismic, but maybe up in your third story, the load combinations will actually have seismic governed over wind. So you have to run both. And what we're finding, as I'm sure you have found, is that as soon as you clad a building in masonry, or you have relatively heavy floor loads, maybe you have mechanical equipment or storage, seismic governs in one, if not both directions. So reducing, or being able to use a higher R to reduce your other forces, particularly foundations, yields a pretty good savings, which is kind of what I talked about in a lot of those AISC seminars. We had done a number of case studies to show that.
Yeah.
So as far as your question about what really spurred the idea behind our device to begin with, when we were looking at doing those bolted components, we recognized bolting BRBs would be advantageous because you could potentially unbolt it and put in a new one. But the issue with that being it's pretty hard to get a 5,000 pound, 30-foot member in and out of the building.
Out of a working
right?
building, yeah.
So we had, through AISC, I actually wanted to teach at the time and started pursuing my PhD work, which included in part bolted testing of BRBs, but we were also looking at bolted testing of WTs and moment frames. And that led us to, more and more of the replaceable fuse type component, that you could have bolted elements in a building that see most of the damage and hopefully have something that you could easily unbolt and replace and salvage the rest of your structure. Whereas most of mainstream seismic design is focused around damage occurring in primary members, which makes it very difficult to repair. So that was some of the fundamental work behind it. As we had done that PhD research, I was working with Jay Puckett, who was at University of Wyoming, now is at Nebraska. We actually got to kind of a moment connection device that we had looked to patent, and the more that we moved in that direction and looked at it, we realized we could probably change that and manipulate it more to be very effective in brace frames. And because we were, in our case, kind of a specialty component where we did very specific geometry, we knew that we could control the force level and get it down to what we weren't able to do in BRBs.
Yeah, that was the basis for the fuse that you have now.
Right. So that's what really led to it. So it was kind of a long road of a number of projects and circumstances sort of falling in the right spots.
Yeah.
I can definitely say, looking out over the long run, we probably had no idea what we were doing at the time to qualify. So.
Oh yeah.
Starting with, you had the concept. Do you immediately go into testing some sort of prototypes, or is it, find an element model of your concept and see if it kind of works in that sense?
Interestingly, it was a little of both.
Yeah.
So FEA played a big part of it. I mean, really, our particular product, it's difficult to describe, but the fundamental mechanism behind it is fairly simple. I mean, what we really started with was the bending of a WT flange, right, where the stem pulled on it. And so we really took that sort of beam, fixed beam behavior. That's what it's really rooted in and based in. So you could do a lot just with hand methods. But then FEA started to let us parametrically look at a number of things. Then the issue with FEA is that it's very hard to take it through the cyclic regimen that you need to do per AISC 341 that's really required to qualify these things. So that's hard to do reliably. So then you end up getting to testing. And so what was interesting there is we finally got the geometry that we wanted to begin cutting out a plate just to test that, which sort of raised the epiphany of, well, why would we just cut these parts out of plate to test? We can make the whole thing out of this, right? And have any geometry that we want. So it migrated from it actually being less expensive for us to test these different geometries and plates than it was to spend the time doing FEA on all these different items. So,
wow.
So that moved it that direction.
How many geometries did you go through?
Oh,
in each direction?
there were a lot, yeah. And then finally getting to the series behavior, I mean, I'm sure we had at least 30 geometry concepts that we probably considered before we landed on one that could actually meet the regimen.
Did Wyoming have a water jet cutter that you could
University of Wyoming did.
Yeah.
That's
nice.
That's a great question too, because we didn't start there. I mean, we had looked at castings, we had looked at all sorts of stuff. Fortunately, as you start into a P695, you have to get a peer review panel. And through a lot of our contacts at AISC in the industry, we got a really strong panel. We were fortunate enough to get Raphael Sabelli with Walter P. Moore and Mike Engelhard down in Texas at Austin. But we also had, and Farzad Naeem is out in California, advisor to the city of LA on a number of things. But we also had a gentleman named Bob Hazelton who's with Herrick. And really, really smart guy out there, and he was advising us a little on some of the constructability, in addition to what Puma was doing. And so he really pushed to, castings are great, but there's so many controls and so many different things, which companies like Castcanex can do, that may make that difficult. He said you really shouldn't abandon the idea of plate, because we can do a lot with plate. We can get a lot of different materials, and so we really went back to plate for that reason, but we're really made the decision to stop focusing on trying to get the material to do more and maybe try to get our processes and geometry to do more. So one of the real issues with seismic, and the whole reason that we try to push the yielding away from connections, because we know that when we weld, we create a heat affected zone that really reduces the inelastic cumulative inelastic life of the material. So you have the same thing with thermal cutting, and water jet cutting doesn't suffer that problem. So we were really looking at every advantage. It's like, all right, we want material with decent toughness. Let's try water jet cutting it. Let's try a geometry that spreads it out over several different elements. Let's even look at grain direction, all sorts of things that finally led to where we landed. So that was a long road as well.
Yeah. Now, what does this timeline look like? conceptual to now? What are we looking
Well, looking back, no, I mean, I would say from when we conceptualized it, which dates back to, I think, 2012, when we probably thought we really had something. What we did in my PhD work actually dates back to 2010, 2009, so we're going back a decade now, from when it probably really started to when we were actually had something that we could test and worked. That was probably closer to 2013, and that was like just the component test. And then the interesting thing, I mean, a lot of people that are trying to develop things have frustration with what the code makes you do. We were very analogous to BRBs in our behavior. So we used 341 and the testing requirements that are in Chapter K for BRBs as kind of our basis. And if you've ever read those, they make you test the brace assembly itself, but then you also have to do a sub-assemblage test that really simulates and captures the connections at the end. And so the other easy way to do that is full-scale testing.
Yeah.
And so once you get to full-scale testing, you open up a whole new set of problems that you probably never thought of, right? Because you have all these stability issues that start to contribute. So then there was a delay trying to get those sorted out and figured out. And then we finally got there, and I think it was 2016 that we completed our peer review process, had all of our testing done, coincidentally had our patent approved at the same time. So all of those kind of fell into place right at the December very end of 2016. So
Cool.
So you've got really 4 or 5 years between when it was conceptualized and really starting to make an effort to look at it to when it was actually something marketable.
Yeah.
And then the effort even beyond that is even greater, right? Which we could talk a little bit about. So the code path is what's interesting. So in many ways, our component, a replaceable fuse component for brace frames, there's a corollary to that. I mean, Simpson's yield link technology, right?
Yeah.
Is similar in that you have a replaceable fuse element where most of the deformation is isolated to that element. The whole system is built around everything else being stronger than those elements and no damage to beams or columns. But it's applied to moment frames, and ours is applied to brace frames, but fairly analogous in a lot of ways. Now, the one advantage they had is that they were qualifying as a special moment frame, which has a path that AISC created to pre-qualify connections and get them in AISC 358. Pre-qualify connections for special and intermediate moment frames.
Right.
And that's what the CPRP that I'm on and haven't always been on, but was recently too, that's what they were built to address. Was AISC was very forward thinking and recognizing that there's a lot of ways to meet the performance we want out of a special moment frame. Let's provide a mechanism to get some of these things out there and make this economical. And so they had that mechanism and have followed that, as well as going through ICC, but we didn't. There is no CPRP or corollary for a brace frame or even a shear wall system. So you're left with kind of limited options. One is you could try to get your own line in the code, in which case it's hard to make it proprietary.
Right.
And a lot of the times, you rag on, hey, these people just want to make this proprietary to try to make a lot of money, right? But the reality is the amount of time and investment that goes into this, unless you have an organization, a big public entity like an NSF grant or AISC or something like that, it's a lot of effort and expense. And so those people need to recoup that in some way on the back end. So that's not all bad, and that's part of why AISC specifically allowed those. A lot of different proprietary connections that were in there was they recognized there were well-behaving systems that they really wanted to get out there that could be economical and provide terrific performance. So they built that, but they haven't had anything like that on the brace frame side. If you look, special concentric brace frames are very prescriptive requirements, right?
Right.
I mean, that's not a performance-based system at all. It's exactly, this is the mechanism, and here's how you have to design your brace and everything in it. BRBs get closer to that,
Mm-hmm.
you know, in that they have a cyclic regimen that you test. But it is still centered around the idea of you got a yielding tendon and it's in a buckling restraint mechanism and all of those things. So it's not overly generic.
Mm-hmm.
So if you want to get your own line in the code, that's one, you have to get over the proprietary aspect because you're going to have to write that very generically. But second, and probably a bigger issue, is the amount of time it takes. If I wanted to get in, I was jotting it down before you came actually, if I wanted to get into ASC 728, right? Because 22, you're not going to get in,
Yeah.
already too late.
Yeah.
You would have to have your ducks in a row and be submitting to ASCE 7 BSSC, the Building Seismic Safety Council,
Right.
like this year.
Wow.
And so then that wouldn't even be adopted till IBC 2030, right? So we're talking about a decade out.
Yeah.
So fortunately, and so that's why a lot of people in moment frame systems have gone through the 358 pre-qualification path, because it's still a long process, but it's a lot faster than that, right?
Yeah.
So then what do you do in brace frames and shear walls? And so ASC 716 is the first to really recognize. ASC 7 has always recognized alternative systems, but it was very generic in that it stated, you need to develop a system and have sufficient analysis and testing to prove that it's analogous to something already in the code. And it's always subject to AHJ approval, with no real definition on what it took to get there, right? I mean, so that was daunting. ASC, and so in AISC, we recognized that we had an issue there with alternative systems, that we really didn't provide a mechanism for it. So we had talked about, hey, can we actually direct people to FEMA P695? That's what it's made for, is developing new systems. And fortunately, we had some very smart people that were also part of ASC 7 at AISC. Jim Harris was one, who's down in Denver, but Jim Malley, who's now head of the spec committee for AISC, Bonnie Manley with American Iron and Steel Institute, and then John Hooper, who's with MKA out in Seattle. They were all on that code committee and recognized that this isn't just a steel issue. This is every material. So let's talk about getting this into ASC 7. And so they did. So ASC 716, if you look at that, now there's a whole new chapter in 12 that's specifically devoted to alternative seismic systems.
Right.
And then if you go to the commentary, it gives you some descriptions that are straight out of P695 without saying it. And then if you go to the commentary, it says, you should use P695, right?
Yeah. So you have a path.
So then you have a path. That's exactly right. Now, the one issue is that path still requires AHJ approval. So you can run through all of that, which is where we have been for a while, but you still have to get the AHJ and the engineer to buy off on it, right? So Jim Harris was actually working on a specialty system, very unique system that isn't, I mean, ours is as close to equivalency as you can find, right? It meets all the performance characteristics of a BRB. Jim Harris was developing a true dual system for light gauge, kind of run by Prescient, is who has engaged him to do that there's just nothing analogous to. So they recognized that they really needed another mechanism. And fortunately, ICC has been forward-thinking enough as well to recognize, hey, we got to give people a better mechanism to get new, well-performing products into the mainstream, kind of like what AISC has done with the CPRP. So they created this new acceptance criteria that Jim primarily authored, called AC 494. And what AC 494 does is it specifically spells out, it adopts all of the aspects of FEMA P695 as an acceptance criteria. Now there's some things you still have to do. If you want to put a system under that, you have to write what they call an annex and get that approved through their public process. And that annex is kind of the more specifically tailored towards the nuances of your system, right? It addresses how you're meeting the requirements of FEMA P695 for your system. So in our case, it basically says, well, you need to do component testing and full-scale testing per the BRBF regimen that's in 341. So that's all spelled out in there, but it really speaks to a brace frame element with ductile fuses that are used to connect that brace to the gusset, right? So you have to get that approved through the public process, but then that gives you a path once you have an acceptance criteria to get an evaluation services report. So an ESR, just like we get on a screw anchor or something like that.
Right.
So now we have something that you can get a piece of paper that building officials generally look at and say, oh, yeah, you
There it is.
we're good to go. I accept that. So we're actually in that process and nearing the tail end of that. So
Nice.
we will hopefully have an ESR, as should Jim's system, both of them this year. In our case, hopefully not too far beyond June or July. So
Very
we'll see
cool.
how that goes. So.
Going back a little bit, I was going to ask, what's the peer review process like? Is this, you're presenting them with the data that you got from all your tests and they're sort of reviewing, or is there secondary testing? Is this...
Can be a little of both. A good question in that one of the interesting things is now that they have that AC, of course it wasn't there when we started. So a lot of our stuff is sort of retroactive with them. The way AC 494 is written is that you're going to get this peer review panel, but a member of ICC will be a part of that. And so in our case, how it's occurred is that most of that peer review was complete. They're presented with all of our stuff. There's an ICC representative that can ask whatever questions and revisit any of that. But it was a little different in that most of the peer review process was done by the time it went to ICC. But your question in the peer review panel usually consists of at least 3 members plus a representative from ICC if that's the route that you're going, and they're intended to be involved from the beginning. So you engage them, and where it becomes really important is, yes, they don't need to be there for your tests, but they want to review your test setup and make sure it was done reasonably and right. And ICC will take that further and really suggest that your test should be done by a certified lab, at least some of the component items. And then they're going to review your analysis and be involved in that. And ideally, it's a very interactive process. In other words, you have ideas, you're starting to develop things, trying to be respectful of their time. Because you're paying them, so you have that interest as well. And if you have a good peer review panel that's qualified, which is a requirement, they ask a lot of really good questions, and they also give you a lot of guidance to further, and that was certainly how it worked in our case. So, they would ask questions that I hadn't thought of, and then you go do more analysis or maybe more testing to satisfy that until you get to a mutual agreement. Probably the biggest component of the P695 process that they need to be a part of is when you look at that, there are some subjective rankings. The nice thing about FEMA P695 is that you can do very little analysis and testing or a lot of analysis and testing. And what it does is it'll allow you to do little, but it'll punish you with a very high uncertainty. It'll recognize that you have high uncertainty. So what it then does is analogous to increasing your factor of safety. You have to achieve what's called a collapse margin ratio that is much higher than if you have very rigorous analysis and a lot of testing so that there's less uncertainty, then your collapse margin ratio gets a lot lower.
I actually did see that table in 695. It's like a beta factor, and it's
It is.
0.1 to 0.3 maybe, or something like that.
Right, and it's actually the combination of several. So there's one on the ground acceleration records, which that's embedded in the methodology, so you don't have to do anything in there. But then there's one on your test data, and so it's a subjective ranking that you're working with your peer review panel on 2 axes of whether it's robust and rooted in sound engineering practice and all of these things, or if you're basing it on external test data. But the point is you're ranking that on, does it fit poor, medium, high? What is the uncertainty? Where do we really fall in there? And so they work with you to come up with where you really fit on each of those, because it is subjective.
Yeah.
It's not a numerical scale. Then based on that, you get that uncertainty. So they have one on testing, and then you have one on your analysis. And then you have one on your design provisions, because you have to develop those, right? And in our case, that wasn't too bad because they were very much based on what's already out there for BRBs.
Mm-hmm.
So that one we have very, very little uncertainty, for example. And then you're correct, you take all of those uncertainties and combine them to a total one. That defines what your collapse margin ratio needs to be.
Cool.
So the peer review group, is instrumental in making sure they're comfortable with how you've ranked those.
Mm-hmm.
So in our case, fortunately, we had some of the benefits that we had were our device provides a really big open balanced hysteresis. So that makes everybody more comfortable. We don't have,
Some
pinching
yeah,
effects,
pinching,
right?
yeah.
We don't have, hey, this thing's way different in compression than tension. I mean, all of those things to address. So that made a lot of those easier, and
Yeah.
definitely easier for analytical modeling.
Yeah.
But the other nice thing is that it just gave our group greater certainty in the analysis that we were doing.
So it sounds like a peer review panel is a lot like an academic advisory panel for a PhD or MS or something,
in many ways.
kind of guide you a little bit more involved than I expected, I guess.
Yeah. No, that's very true. That's a good analogy of how to look at their involvement, But just like your advisors, they're also busy people. Doing a lot of stuff.
You don't get all their time.
So
You have to get the jurisdictions to accept all this.
Mm-hmm.
A lot of times, have you had success with that so far? And have you guys gotten into some structures?
So we did, and in many cases it was kind of a proof of concept, but we had a storage building that was actually in Cheyenne, Wyoming, which kind of illustrates the point. This was one where it was design build steel with Puma, which is kind of how this all worked out and went together, where the information was given to the GC very specifically, conveyed to him what the genesis of this system was, where it came from, what the advantages were. Do you want to entertain it? And they did. So effectively, two designs were produced. One that was a traditional RF3 system, and one that used Refuse, our product. And so Puma gave them the steel costs, and then they were also given the foundation designs associated with each. And they were able to compare that and make a decision outside of, because we're in lower moderate seismic, the benefits of replaceability and performance don't strike as true to anyone. You're just like, why would I do anything different than what I'm doing? But in this case, is entirely an economical decision. And so they decided, yes, that's what we want to pursue. So we did need to develop a packet to make sure that the building official and department was aware of everything that was going on, and how we were approaching this. And I will say that effort depends a lot by your building department, right? I mean, when you're trying to do something in LA, you've got building officials who are engineers who do this stuff every day.
Very informed.
Right. Versus, in our region, it's just not what they're used to seeing, if they're involved in structure much at all. And I mean, I can't say in Wyoming, a lot of the time they don't have peer reviews or structural engineers on staff to review a lot of those. It's somewhat general knowledge. So in that particular case, it was more of, hey, look, if the EOR is good with it, we're pretty good with it, right? And probably in Denver, it wouldn't be much different.
Right.
So that varies a lot, but obviously, if you got an ICC ESR, that makes everybody happy.
Yeah.
So.
Yeah, have something to back up what you're doing and specify on drawings. So.
Yep. So that's the one that we've put in. It's been a little less active in marketing at the moment, just because we've really been focused on the ESR.
Yeah.
Right.
So we were holding off on really pursuing any more buildings till we had that.
That's cool. And so the system starts at 30 kip load and goes up to mid twos. Is that right?
So
Something like that.
So the system, the plates that we produce are always in pairs. So they sandwich the gusset in the web of a wide flange brace. And so one of the things we like about that is there's inherent redundancy there. you always have to fail more than one element before this thing would actually fail. And so a pair, a plate each side, starts at an available strength, like you were saying, of 30 kips. That's feet PN. And then as you add plies, which means we just add another pair on the outside of those, you go up in 30 kip increments. And it's been qualified from obviously the lowest range to 30 kips up to our highest configuration we've currently qualified of 210 kips. So that's actually 7 plies each side.
Yeah.
And is that a geometry best with a W12? It's like what I read through is that's the size you kind of are supposed to use for your braces.
Right, and it did fit very well with that. I mean, we actually tested some with the W14, but because most of them we qualified with W12s, that's why we put that in there. It isn't to say that there aren't other configurations or you couldn't do something different. But again, it goes back to the whole qualification and certainly you kind of want to pick your battles, right? Because if you deviate outside of that brace, I can say, based on everything I'm seeing, I'm quite confident it'll perform well, but the question always comes back, have you tested it? Well, no. So it sticks with what we've tested, right?
What will a fabricator have to do in the future to qualify to produce these? Will it be, more local shops and shipped, or will these be able to be manufactured kind of wherever you're doing your project?
So the intent, the way these work is it's what we would call in the industry a buyout item, right? So the fabricator still produces the brace and the gussets and provides the bolts and all of those things. The refuse product is provided to them to put on the brace in the shop. The people or the plants that could actually, so any fabricator can use it, right, when it's specified on a job. But the people who can actually produce refuse, that actually in the world of the ESR, you, as part of that process, need to qualify specific plants to do that. So Puma Steel is the plant that's qualified under the ESR. Others could be added down the road, but they would be the producer or provider of those. So
very similar to the BRVs.
Exactly.
Yeah.
You got a supplier that provides those. So very similar to that. Yeah, I mean, interestingly, we had thought about the mechanism early on of, could you allow anyone to do these?
Yeah.
And if they're AISC certified, I mean, in our case, it's not rocket science. We've worked very hard to make sure that all the processes, both in the fabrication and implementation, are commonplace in the industry. I mean, it's using all the same materials, technologies, bolts.
The fuse are grade 50, right?
Right.
And it's just
and it's
thermal cut the
A325
outside
bolts and all the tolerances are
Yeah.
per AISC code of standard practice and all that good stuff. So there was potentially a mechanism where you could allow anyone to do that. That actually is a little at odds with ICC, who really wants to qualify each plant. So there was a little of a meeting of the minds there, and it made sense in the end. I mean, obviously it's in our interest and everybody's interest that you have someone producing them that understands it, has done it before. It's demonstrated. In this case, you got the same entity producing it that produced everything for our testing. So there's definitely some sound benefit there.
seems like shipping these isn't as big deal as
No, that's
BRB or anything
right. I
really.
mean, yeah, exactly. These are the parts themselves weigh anywhere from 30 to 90 pounds each one, depending on the configuration, and they're 2 feet to roughly 5 feet long. So they're pretty easy to ship. That's one of the other nice benefits too, though, is that they can go in and out of a building pretty easily.
Yeah.
Right? They can get in an elevator. They can go in stairwells. They can go up ship's ladders. So they can really get into almost any part of a building. So replacing them is actually realistic, much like Yield Link. The other nice thing is that it lends itself very well to retrofit.
I was going to ask that question, yeah.
Yeah, exactly. You can get them into any buildings, and at that point, you're not limited at all to steel buildings. It's one of the nice things too. We have, ASCE 41 now, which has really come a long way in being a comprehensive document on how we assess existing buildings for seismic retrofit and what we need to do to upgrade them. And When you have a lot of test data on a product, that makes it a lot easier using those methodologies. So.
Yeah, definitely. Yeah, that was pretty cool that, the idea of having everything bolted, so, your column, everything in these connections are bolted, so at a later date, if anything were to kind of get out of the screw or maybe have a hinge crate or something where beyond what it was designed for, you could just come in and re-bolt in a new one. I think that's
Right.
really seeing the whole story there instead of just the fuse element. So
Yeah, I appreciate that. That is kind of the idea.
Yeah.
And really we went with standard oversized holes in a lot of cases, which kind of accumulate in your tolerances, right? Because you got a bolted connection of the gusset to the fuse and then another one of the fuse to the gusset. And so that was intentional not only to allow for fit up, which we often do in vertical braces that are bolted anyway, because you got beam overrun and underrun you got to account for. But the other thing it does is if you do have some drift in the frame and you want to unbolt and put in a new one, you've got some room to accommodate whatever drift or out of plumbness may have occurred there.
Yeah.
Obviously, if it's too big, if it's so big you can't accommodate it with that, then you probably need to
Issue
do a
with the builder.
replumbing anyway. Yeah, exactly. Which I'm sure is not a trivial deal.
Yeah, certainly. And then in design, you can use different software packages and sort of tricks around things. Obviously, it's not probably in something like RAM yet, but you could sort of trick around the software.
Wow, you really got into it.
Yeah.
No, you're correct. It's not. Most of our procedures, you don't have to do anything inelastic or nonlinear, right?
Right.
So because you use just a C sub D factor to approximate the inelastic behavior. So really we're doing an elastic analysis to begin with. So the elastic behavior is pretty simple. It's just a spring on the end of the brace. So you're correct. You can, in some software, just put in a spring constant. Other ones you could put in, say, a 1 foot long element of a given area that gives you that same stiffness. Exactly, there are a number of ways that you can do that, short of having a full blown plug-in.
Yeah. Have you seen any software that you prefer as far as kind of altering the performance, or it seems like if you're putting a spring, almost anything could do that.
Yeah, and that's part of why we put some of those in there. The other thing you could do is, when you know your brace and you know those end elements, you can calculate an effective stiffness and could assign that to whatever brace member's in there, right? In the overall deal without messing with the end. So the easiest one I would say is your SAP and ETABS. Just let you put a spring constant in right off the bat, right? And I think RISA 3D might let you do that as well. If it didn't, I think it does now. I think it's actually there. RAM's a little different animal in that then you would probably take the other approach of putting in an equivalent stiffness member. The other thing with RAM, they've come a ways, and we'll see what the future holds, but they've got a full module that'll handle BRBs very well.
Yeah.
So hopefully as it becomes more mainstream, it'd be easy down the road to just have them kind of move that technology over to adopt this and do that full design and reflect all that stiffness as well. So I don't know that I have a preference. That was part of our intent, was to try to make it so that you could, whatever software you're using, you could hopefully be able to figure it out and implement the system pretty easily.
Is there sort of, once you're more in the market, intent to sort of help engineers get the system into their building, much like Star Seismic or
Core Brace
now, kind of does a little hand-holding to get their products in? You think it's a simple enough design that you can basically just hand it off, and with the design guides you have, basically take it from there?
Yeah, the contrast in the approaches a little bit is the BRB guys. What they do is a lot of the time they'll design the connection, right?
Right.
At least the connection to the gusset and the gusset to the main members, not necessarily your beam to column connection. So they do assist there a little bit, and then they work with the engineering, giving them the stiffness. But part of the reason they do that is because they don't know what the stiffness of their brace is going to be yet until they understand the length and how long their yield link is going to be once they get their connection figured out and then design their connection. So in that case, part of the reason they do the hand holding is because they they need to.
I never thought about that.
So
Okay.
so it's actually a little bit of an iterative procedure.
Yeah.
With BRBs. You run through a design using some assumptions that they help you with and give you. Then they finalize it and tell you what the
Rerun
stiffness
again,
is, and you rerun it to make sure that that's valid, right?
That makes
Um,
sense. Gone through that procedure, and I just thought, I don't know, they were just being very helpful.
So part of one of the nice things about ours is that the component itself never changes. So that behavior is always known and tabularized. So the engineer can actually do the whole design without having to involve us. Now, novel structures would absolutely help with any of that. The other thing that allows is because the probable force is always known for the different systems, is we've been able to pre-design most of the connections, and those are in there. So you can design them conventionally any way that you want, or you can literally just say, hey, go see the Refuse design guide and detail it per what's in there on the connection. So it does afford that opportunity. I guess the other model that you're talking about, which we haven't really gone there, is, side plates got their own mechanism, which is really to say, yeah, we'll take over the design from you, and the fabricator will pay us to do that. Back then, right? There's a fee to use our product to do that, which is attractive for. I mean, it's got its advantages, and certainly in some areas, and it's definitely attractive for engineers on the West Coast, because they see it as. There are certain buildings that may fit very well, and in that case, they get kind of a peer review, if you will, from side plate on that. But really, they get to take part of their design scope and say, "You guys handle that." Oh yeah. So that all works well on the design fee side of things. But of course, you're paying for that on the back end on the construction side. So. But we have not looked to adopt that model.
I just realized the table's made with wide flanges.
That's what's nice, having worked for a steel fabricator.
Yeah. When did you switch from Puma to Martin Martin?
So I was actually at Martin & Martin to start. I started the Wyoming office up there years ago, and then went to work for Puma in 2006. Worked there through about 2010. So that was through really good times and really rough times. Session. So, and then 2010 is when I came back to Martin & Martin. Was their tech director for a while. So
cool. Was the time at Puma Steel? I mean, that's not the same sort of design work Martin & Martin is, I assume. I mean, is that more detailing?
You guys being practicing engineers, I mean, you'll appreciate, it was kind of funny. A lot of my colleagues at Martin & Martin, I would tell them I actually do way more actual engineering numbers for Puma than I ever did, with all the drafting and all the stuff that you do in the consulting world. So, I mean, the time at Puma was great, not only because for me, I was keeping up with all the codes and feeling like you're really on top of it, knowledgeable in every material is daunting. It's just getting harder and harder to be a generalist.
Oh, yeah.
And so that was part of it. I really enjoyed steel and had a desire to focus on that material, and it allowed me to do that. The other insight it gave me was just a lot of knowledge and insight into fabrication and erection procedures, methodologies, all the things they deal with. So it no doubt made me a far better engineer. So I would recommend to any young engineer, any opportunity you have, whether through internships or even in practice. In fact, we've even talked about trying to set up some sort of exchange program with a contractor or a subcontractor of some sort, because that knowledge you get working for those entities, even in the short term, is just, it's invaluable. I mean, you guys know we live in a world where when we draw a detail, all the lines and tolerances are perfectly straight. There's no flange till we rev it, right?
Right.
But when you get out and actually watch guys trying to build it and try to weld something and understand, an overhead weld is a real pain in the butt.
That's
really hard.
Get why they don't like that.
Having construction experience seems to be just really important for getting a grasp on detailing and, getting good understanding of constructability.
Yeah.
I wish I had a little more. I mean, it's hard to go back.
Well, and even sequencing. I mean, I'll pick on the GCs now, just because I've interviewed many of them. and very upfront. I mean, I have a lot of good GC contacts, but when you talk about if there's a feedback loop from their field guys back to their pre-con guys, they're like, no, we're terrible about that. You know, our pre-con guy remembers who gave him the low bid and nothing after that.
Yep.
That's why they get used again, and it never gets back to them how many headaches that sub may have caused them in the field. And yeah, it's kind of funny. So it's, you know, even in the GC world itself, they could probably do with a little more of that field experience too.
Absolutely. That kind of goes perfect into our kind of question we ask everyone, and that's you know, for new engineers, what's like 3 good tips that you'd give someone that's starting off, or however many.
Since their guidance counselor already failed.
Right, like, you know, what's a lot of it is mentorship that we've found and have talked about, but you know, as a principal, what would you like to see or teach or know or?
So one, I give engineers who haven't even got their first job yet, which may not be quite what we're talking about.
No, that's perfect.
You know, I like to recommend, because I know a lot of them struggle with whether or not they should work for a big firm or a small firm from the start, right? Because a lot of them, you know, have a tendency to want to migrate to wherever they want to live and be happy, which is important. My advice would be, I would try to work for a large firm first, because you can always go to a smaller firm, but it's a lot more difficult to go from a smaller firm and then move up into a bigger firm. They generally have, you know, training programs and ways to do things, and that can be a little more difficult. And so that's often my first advice for people that are entering the field to begin with. The second one, I'll reiterate because it's that important. We've already touched on it. Whatever mechanism you can do to gain a little bit of construction experience, even if it's, you know, working for a house builder in the summer while you're in school, something like that, that's super valuable. I would encourage any of them to do that. And my final advice would be, you know, we're in a world where we do. I see engineers doing way less engineering than they used to. I mean, we spend a lot more time in Revit or whatever those things are, producing the job. But I would focus on, especially as technology has grown and we have more and more robust tools and rather difficult mandated analysis methods, like the direct analysis method, for example, that is required, yet I don't know if anyone actually understands it or does it. But is to really keep in mind and try to focus on keeping things simple. There's a lot to be said for finding a conservative solution that makes sense to make sure that you're validating a more complex solution in all cases. You always need to think about behavior. Check your deflected shape. Try to find a very simple, fundamental way to validate what you're doing. And I find that helps even in your discussion with your senior engineers and in all contexts. If you can bring things back to that level, it just helps everybody's understanding.
Yeah.
So,
what would you say if you're looking to hire an EI engineer in 1 to 3 years or whatnot? What do you look for when you're scanning those people?
I mean, I'll answer that first with our company, you know, has definitely migrated towards more of an emphasis on looking at their technical skills. And so my suggestion would be to really move up in a company. You need to have that balance of both. So you're going to need your technical skills to get in the door, and I absolutely look for those. You know, I mean, we want to understand that people have good technical ability, and normally we get that less out of an interview and more out of talking to their advisors and the people, you know, who they've been working with. But then their ability to communicate in writing and be able to communicate in person when you sit down, and just like I said, be able to talk about a complicated problem in layman's terms or so that anyone can understand it. That's really valuable.
Yeah.
That to me, that you're hired if you have an ability to do that.
Yeah.
So
Is Martin Martin a master's preferred firm? I mean,
they are.
I know a lot are going
and
to
in reality,
Department.
yeah. And it used to be, you know, like SA Mural was an example too. They were, but it was more of a weed out
Yeah.
as much as anything to begin with. So they didn't necessarily hold true to it.
Mm-hmm.
I would say in recent years, Martin & Martin has held true to that. One of the benefits there is that the process of, and not all of them have that route, but the process of writing a thesis, researching and writing a thesis, helps accomplish what I was just talking about.
Communication.
You have
Yeah.
to learn how to communicate technically, and that's just a huge part of our job.
Yeah.
And I'm sure you guys know it. I could spend all day doing nothing but email, and you can get yourself
Yeah.
in trouble just
Yeah.
as easy as anything, right?
Absolutely.
I've got one more for you. As far as a master's degree, do you think it's beneficial to do it directly after undergrad, or is it, to work for a little bit and go back?
I think it's actually really hard to work for a little bit and go back. And it's for a lot of reasons.
Yeah.
From an engineering point of view, not as much, but just because of where you end up in your life. I mean, you inherently gain responsibilities and need the paycheck, and it's not easy to go back. I think there'd be value in it because by then you've really figured out if this is right for you.
Yeah.
And it's good to have an even greater knowledge base before you go back and do that. But I think realistically, plus what you do in a research, and most master's degrees are very research focused, right?
Yeah.
You have a research project. That is very departed and different than what we do in consulting engineering. So there is some value in staying in academia, getting that done, getting that research aspect, developing those communication skills, then going out into practice. That said, some people that's not even an option because you've already taken the other route. So I would encourage anyone who's interested in going back to get a master's to do that.
Yeah.
I mean, it will be very valuable. There's no way even a very senior engineer would do things less than that, right?
Yeah.
Absolutely.
Nice. Yeah, that's the answer I've heard many, many times. Is you might just want to do it while you're there. For a lot of reasons, it's hard to go back.
It's hard to go back.
Yeah.
I mean, I went back to get my PhD,
Yeah.
and that was. I do not recommend that. now.
No.
Absolutely.
That's too much.
I saw they were coming out with a wind-based
Yeah.
performance design.
Well,
and
that-
CPP, I think, is doing a lot of the work.
They are.
Yeah.
I mean, that's an interesting point where we saw, as you know, in this area we design for R3 most of the time, right? And there's some inherent ductility there, but the big issue with it is that you just don't know what the weakest link is in any given design, right? It can vary so much. It's very hard to quantify what that could be. So you may have some systems that have some ductility, and you may have others that none at all. I mean, it's just, it's governed by that one weld by a long way.
Yeah.
And so that's a little different than even concrete. I'll give that system credit, not for shear. For shear, it's a pain in the butt.
Yeah.
But flexurally, you're just required to have inherent ductility, right? I
Yeah.
mean, you're required in base
In the nature
concrete
of concrete, yeah.
right, to develop the reinforcing. So one of the directions that I know the code is going, because AISC just awarded John Judd up in Wyoming the Millick Fellowship on looking at inelastic design for wind. And what that really is focused around is that, hey, let's design for extreme wind events, i.e. a tornado, which come to find out that half of the wind loads we design for as you get up in the foothills are approaching tornadoes.
Yeah.
But let's design some of those taking advantage of inelastic design. So it's lending itself to methodologies. I don't know if it'll end up looking the same, but very similar to R factors and getting to reduce your loads in some fashion based on the ductility you have. So that being said, there's always been discussion about, does RF3 have a shelf life? And I would say as that gets more mainstream, probably so.
Wow.
I mean, certainly a lot of your people on the West Coast RF3 just makes them nervous. They're just like, not that it's allowed out there, but fundamentally, when you move outside of it, their belief is every building should have some ductility we can count on. And the wind loads or provisions or direction of them would move you more that direction.
Absolutely. Yeah, that's all I
Kind of
designed was
rushed
high
into here.
seismic out there, and I came out here and first project, this is R3.
A what?
3. That, I didn't even know that was in the
You
code
do
book.
that?
You know, like R of 8 for everything, isn't that? Or
Wow.
your 6 is what we do. And
All right, so that was our talk with Patrick McManus of Martin and Martin.
man, he is so experienced and has got so much knowledge on all these systems.
He's a
And
smart guy.
this refused brace frame.
That's such a cool system, and I think I understand a lot better now. I mean, hitting those lower load limits is really smart.
What I think as a young engineer that you can really take out of the conversation we had with Patrick was the whole idea of the ICC ESR reports for different types of systems, being able to use those to be able to go to your code official and prove the system.
Absolutely, yeah. So check him out and check out Martin and Martin if you don't know the company. It's really impressive. And thanks for joining us this week.
You know how to reach out to us, and later.